Hi there, my name is Banda. I'm going to be doing a simulation of methanol water system. This falls under computer-aided design as applied to distillation. This is one of my favorite topics or expertise, that is distillation. So I hope you enjoy. A step-by-step guide to successfully model any distillation column. So the principles presented here can be used for any distillation column. Distillation is the process of separating the components or substances from a liquid mixture by using selective boiling and condensation. So this boiling and condensation happens in each and every tray. Optimal design of distillation columns is complex because of many entangled design variables, such as operating pressure, reflux ratio, number of stages, product specification. These variables need to be optimized. A typical situation in distillation design is that the feed conditions are given. So you're given your flow rate, the composition, temperature, and pressure. Then your stream becomes fully defined. The desired compositions of the product streams are also typical, known or given by whoever is requesting the design. Design requirements. I'm going to present to you an example of a typical design question. So usually we are given the flow rate, in this case it's 5,000 pounds per hour. Then it's 50% molar methanol, 50% molar water. So these are equimolar, which means they're equal in terms of moles. We have a temperature of 80 degrees Fahrenheit and 20 pounds per square inch gauge pressure. Column performance. So in this case, methanol is the low boiling component, so you find it in the distillate, whereas the water, you find it at the bottom. So the methanol stream purity, which is the distillate, needs to be 99%. The methanol recovery needs to be 99.5%. That simply means whatever weight is in the feed, 99% of that should be found in the distillate. Other information includes available steam for the repair of the boiler. In this case, we have two types of steam available for us. So we have the 25 pound per square inch gauge and the 100 pound per square inch gauge in terms of pressure steam. We also have a cooling water at 30 degrees Celsius, and the delta temperature approach between process and utilities is 20 degrees Celsius and 90 degrees Celsius. I'm going to explain down the slides what is meant by temperature approach. So configuring a new simulation case. So whatever process simulator software you are using, it might be HISYS, Aspen Plus, ChemCAD, Pro2, DWC, Coco, ChemSec. The first step is to open a blank worksheet and add pieces of process equipment. So these equipments include the distillation column itself, the condenser, the reboiler, their pumps, their valves, and add a stream between them. Right? In this case, I'll be using Coco in conjunction with ChemSec. The main reason is because these are open source software, which means you can just download them online for free. But the results, they match with those of Aspen. So if you have Aspen Plus or ChemCAD, you're free to follow the same example, but using those. Optional, you can also define an accumulation vessel for the condensate. In this case, I won't do it. So I will show you what we mean by the simulation environment. So this is Coco, right? The open source software I told you about. Once you open it, it gives you a blank worksheet. So we'll go back to our slides. So on that simulation environment I showed you, you then put your distillation column. This is the pump. This is your pump again. This pumps your product maybe to a storage tank. This is the condenser. This is the reboiler. Then this is your feed stream. So that's your distillate, that's your bottoms, right? So the contents of the drum are assumed to be perfectly mixed with the composition XD. The liquid in the drum is at its bubble point. Vapor boil up is generated in a thermosiphon reboiler at a rate V. In simulation, a design specification has been used to maintain the top and bottom composition of column to achieve maximum purity. So you define what is the purity of your distillate, and also usually define also the reflux ratio, because you have 2 degrees of freedom before your system is fully specified. This can be done by using optimization approach for column feed location, minimum number of trays, and minimum reflux ratio. Selecting optimum feed location is critical to maximizing distillation column performance. Improper feed location of a distillation column can downgrade column performance. The degree of separation is decreased at the same reflux or boil-up ratio, or the higher reflux boil-up ratio is required to maintain a degree of separation. So the objective is to minimize the pre-boiler heat duty, which accounts for a major portion of operating costs, more so that nowadays NH costs are so high, right? Specifying chemical components. Next, we must define the chemical components involved in the separation. In this case, we have methanol and water. So I'll show you how to do it. So you go here to configure flow sheet. Then you press add. We are going to use the T, which is the thermodynamic property of cocoa. If you want, you can use the ChemSep one. There we go. I'll click on new. Then I'll add my compound. So we have methanol. It is a double click. It goes there. Then we have water. Right. Water. We double click. Then it goes there. For now, I'll leave it like that. Then we'll come and continue. Specifying thermodynamics property. Most of the software packages will suggest the thermodynamic property package that suits defined components. More so like Aspen ICs, ChemCAD will do so, but Cocoa doesn't do so. If you do not have any specific knowledge or requirements, it is best to use the suggested thermodynamic package. That's this one only a novice designer. You don't know how to select your thermodynamics model, then you should let the simulation software help you to do so. But in this case, I use the thermodynamics decision tree, and and I selected NRTL, which is the non-random to liquid property package. And I spoke about how to use a decision tree to select a thermodynamics model on my previous lecture. So I won't do it here. So let's go back to the simulation environment and select the NRTL property package. So there we go. We select the NRTL. Name, we can just put methanol. Distillation. Right. Can put whatever you want, right? But it has to be relevant, of course, to whatever you're doing, right? Separation. This is the description. Separation. Methanol. Then you press OK. Yes. One more thing I forgot to do. So I'll go back here and press edit. You need to make sure that your binary interaction parameters are there and configured correctly. So I'll come up here, as you see here, it puts penroxone, but we're not using penroxone, we're using NRTL. There you go. So you have them, both of them. So we're good to go. You press OK. You close the window. It will take you back to the simulation environment. Let's continue with our slide presentation. It keeps on taking me back to the first page, but it's okay. I'll figure out to make it continue, but for now we use whatever we have. So the input streams to the process must be specified. In a simple case, as the basic column described above, there's only one input stream, which is the feed stream. The flow rate, composition, temperature, and pressure of the stream must be specified. We are given the conditions of the feed stream, right? If you're using any additional input streams, such as steam for heating or additional feed, then those streams need to be specified as well. In this case, we have only one input stream, which is the feed stream. Specifying equipment parameters. The parameters for all the equipment included must be specified by opening equipment icons and defining necessary data. I will show you. In this case, you'll be, for example, for your Sytstem, you'll be putting like your feed flow rate. You'll be putting like the composition of your feed and also the temperature and the pressure. If you do not have any specific data or requirements, it is appropriate to make the assumption that both pumps will generate a pressure difference of 5 bars between suction and discharge. So the purpose of a pump, of course, is to increase pressure. So you make sure if you don't have any information at the design stage, you assume there's a pressure increase of 5 bars. So make the specification for both pumps in accordance. We have 2 pumps here, the one to pump the distillate product and the one to pump the bottoms product. Specifying valves. In this case, the only valve we are going to look at is the one at the feed line, right? So the pressure at the exit of the feed valve must be equal to the pressure on the feed tray. We do not know exactly what this is at this point, but we will make an assumption and define it as slightly higher than expected to be on a safe side for the calculation purposes. At this point, it is also possible to avoid putting the valve into the flow sheet and add it later when the column is converged and pressure is known. So for this simulation, I won't be putting any valve, but for the next presentation, I'll try to put my valve and also to put the pumps. After you have converged the column, come back and adjust it. Now you know once your column converges, you know what's the pressure at your feed stage, so you can come and correct it. Right? For other two control valves, use the assumption of pressure drop of about 3 bars, if not defined differently with available data. Specifying column parameters. The following parameters need to be defined. That is the number of stages if you are calculating a non-column and are familiar with the column data, then use the parameter as defined in the documentation. But at the design stage, most of the time, we do not have such information of number of stages. So if not, make the assumption to get the first results. How do we make such an assumption? Acceptable assumptions can be to define 30 trays plus 2 stages for a boiler and a condenser. So which means now you'll be having 32 stages, which includes trays. In COCO, it assumes that your condenser and your boiler are stages, equilibrium stage, right? Which means your vapor and liquid, they at equilibrium. So for the feed tray, again, if you have the non-data, use them. That's if you are simulating a distillation column, which already exists in the plant, right? If not, make an assumption for the moment and set this in the middle of the column. In this case, we have 32 stages. So you put it on stage 16 or at feed tray 15. Later, a feed tray option can be analyzed further and optimized by finding the tray that minimizes the boiler heat input. I won't do it in this presentation, but the next presentation will be on how to optimize your converged distillation column. And you should alter the feed pressure such that it enters with the same pressure as that of the feed stage. Of course, it should be slightly higher so that you can drive your feed into the distillation column, right? So now we'll go back to the simulation column and I'll show you how to specify streams. Okay, so we have the feed stream here, right? We'll put it as, I'll put it as stream 1. Stream 1. So this is your feed stream. Okay. We have a pressure in, we are given a pressure in pound per square in gauge, which is 20. Also, we have a temperature in degrees Fahrenheit. Okay, we'll change that to Fahrenheit. There we go. We have it has 80. We also given the mole fraction as 0.5. Of course, the other one automatically is 0.5. Then our feed flow rate is given in pounds per hour. So we change our units here to pounds per hour. Okay. There you go. We're giving is 5,000. Right. So phase fractions, of course, it is a liquid, right? And it's not at its bubble point. How do I know that? Because if I come to liquid properties, it will tell me something about the bubble point temperature is that, you know, we are not at those temperatures. So it's a subcooled liquid. If you don't know what that is, then you can go find out. Then you press here. So when it's green, it shows that it is a calculated and found the solution. Then we add our distillation column. So we come to your separators. We use the one from ChemSep. We select it. There we go. Right. Double click on it. You go to edit. Then you press OK. Okay, give me a second here. I'll plug in my charger. Yeah, welcome back. As I become more good with editing, I'll avoid such situations. But for now, so when it's ticked green like this, it shows that you do not need to specify to input anything. But when it's crossed like this, it shows that you need to put some parameters. But even if it's ticked, I'll advise you to go on each and every step and see what's there. So keep open, nothing much there. The title, you can put whatever you want there. Components, of course, we selected those as methanol or water. Operation. So it puts 20, but we know we need 32. Yes. And we said our feed stage is 16 years. So you keep on going. Reactions, we do not have any reactions. Feeds, there we have it. Specifications, analysis. You can read that if you want to. Pressures, the condenser pressure. So we'll come back here once I'll let you know how to select it. Back to our slide. We did that. Let's talk about the balance. Parameters, we did pressure. How do you select the pressure? The column top pressure and the pressure drop should be defined. So you need to, when you say the top pressure, we are talking about the condenser pressure. Because you need to condense the vapors which exit the top of a distillation column to a liquid, so that you have your product as a liquid. Also, you have the reflux to attend to the distillation column. So if you have known data, use them. If not, then you should look at equilibrium data for the defined system of components, which means you're trying to find the dew point, you know, given your product specifications. So some designers, they set the column pressure to 1 atmosphere, despite the fact that the reflux drum temperatures are significantly greater than the 323 Kelvin minimum needed to use the cooling water in the condensers. So if you are to use water, you need a minimum of 50s. So it's advisable not just to choose your pressure as 1 atmosphere, but decrease it to the point whereby you can still use your cooling water as the cooling source, right? Or as the heat sink. A pressure of 1 atmosphere will be used for this simulation. Also, a reasonable tray pressure drop is about 0.007 bar per tray. So we'll go back to our simulation environment and define this. So you come back here. Okay, this is our concept. Condenser pressure, remember we said 1/2 here. So you come here and change your units, right, to atmospheres. I come there, I put it atmospheres, press enter. Then I go to my pressure. So already it puts it as 1 atmosphere, as I specify that most designers, they use 1 atmosphere. Then we don't want a constant pressure when we have fixed pressure drop per stage. Remember we said it's 0.007 bar. So I'll go back again, change my units to bar so that I can input that parameter, right? Change it to bar there, press my enter, go back to my pressure. It's recheck again, what was that value? Pressure 0.007, yes. So I'll come back here, put it there. 0.007, right? You press enter. One thing to note, you should know that our pressure is higher at the bottom so that it will drive the vapors upwards, right? So that's why we specify this pressure drop so that we have a higher pressure drop at the bottoms. Okay, we're down then. Heat loss. So here we'll assume that there's no heat loss, right? Key column efficiencies. We'll assume 100% stage efficiency, which is not true. Column specs. Right. Remember, we said we needed to have 99% methanol. At our distillate, right? So we come here and say mole fraction of component, which is methanol. It knows methanol goes out top because it is a lower boiling point as compared to our water. And 99.5% is 0.995, right? And also we're told we need methanol recovery of 99.5% in the distillate, right? So I'll come back to my calculator here. Okay, so if 99.5% recovery of methanol is at the distillate, how many do we have at the bottom? So it's simply 100 minus 99.5%, right? 100 minus 99.5 give us 0.5 divided by 100, right? So it's 0.005. Yes. Come back here. Because you need to make a specification for the distillate and also a specification for the bottoms. Remember, we said we have 2 degrees of freedom. So you come up here, mole fraction of a component. Okay. That's of methanol. Yes, we want it to be 0.005. I'll cross check that value again. Yeah, 0.005. Press your enter. You're done. So this is still cross because our solution isn't converged. So you just press X here. Do you want to set the current input in ChemSep? You press yes. Current configuration is changed. Update code. Say yes. And you press X. You see now it has changed. It has put your stage up to 31. This is 32. So your feed stage here, you connect it to your codon. There you go. And also you connect this. Yeah, this is your distillate, right? So it says top product, bottom product. So you need to specify top product. So I'll call it stream 2. You can put distillate if you want, but it won't be effective when you have main equipments, when you're designing the whole plant. In this case, I'm just designing only one unit of operation, right? Then also you put there. So this is our bottoms. So I'll call it stream 3. All right. I'll try to make it look nicer. All right. So now it's fully specified. You press again. So it's a simple simulation. It shouldn't take that long. It says failed to calculate. I don't know why it failed. We'll go back and check our specifications. Right. Just means it didn't reach a solution. Right? I'll go back, check why. Column specs. Okay. I put here, I want the recovery. No, component recovery instead. So that was the mistake. Let's go try it again and see. Shouldn't give us trouble now. There we go. Let's see. Cross fingers. I don't know why it's doing that. I filled in the wrong field, completely random. Okay. Let's check. Let's go back and check again. Components, specification, expressions, stage, we put it, running that column specs. Oh, there is the problem. It needs to be 0.0. Recovered methanol. There we go. So you need to know how to troubleshoot when your simulation doesn't converge. I'm glad it did happen like that so that you learn how to check for your mistakes. You should be able to. There we go. Boom. So you come here, you go to insert. Want to put a stream report. Sure. I'll put it on the side since there are no many equipments. And you put them there, you put them there, you put them there. Boom. There we go. You know what I mean? I want to put one more thing, the flows, so that we know how much component flows. Now it will tell you in the feed with so much 3,200 lb per hour of methanol, and now at our distillates with 31.84. I will show you further how that is 99.5% recovery. We also wanted 0.995 methanol on the distillate, which is good. And our water at the bottom is that. So we've managed to separate our methanol from water. But then let's go back, I'll call it methanol, methanol, water, distillation column. Leave it like that. So let's go back to our presentation. Let's see how to go. Takes me back again to the first page, but let me see how we do that. It's fine, isn't it? I mean, simulation is fun, is always fun. So condenser or boiler. Condenser, define it as a total or partial if the distillate were removed as vapor. So in this case, we use the total condenser. The reboiler, the vapor from the reboiler is in equilibrium with the liquid bottoms product withdrawn and is a major NS source for the column. As I said, the vapor and the condenser, we take them as equilibrium stages. That's why we inputted the stages, number of stages as 32, even though we have 30 trays. Convergence. A distillation column has 2 degrees of freedom once the feed pressure, number of trays, and feed tray location have been fixed. So at this stage of the simulation, the usual approach is to fix the distillate flow rate in accordance with the composition of feed and reflux ratio. So the normal input is to put your distillate flow rate, and usually you have to do your material balance on paper, then input those. But in this case, I didn't have to do that. It also depends on the complexity of your simulation, and I'll look at those as I present the how distillation works. Then later, once you obtain a converged solution, you can change the specified variable so that the product specifications are met. Again, if you have an approximate data, use them to get the results and then optimize the calculation to meet the requirements. If you don't have the specific data, specify an approximate distillate flow rate and assume a reflux ratio. So the reflux ratio is the ratio between the amount of the reflux that goes back down the distillation column and the amount of reflux that is collected in the receiver, the distillate. The range of reflux ratio is very wide. In practical experience, it can range from 0.3 if it's an easy separation up to 20 for a hard separation. It also varies with the amount of the overhead component in the feed stream. For example, separation of IC4 and NC4 can have reflux ratios from about 10 to about 20, with the only change being the amount of IC4. So the IC4 will influence your reflux ratio in the feed stream, right? So usually the good start is assuming a reflux ratio of 10, getting the column to converge, and then decrease it accordingly if possible. So usually you just assume the reflux ratio is 10 and also input your distillate flow rate so that to achieve a specified distillate purity. In this case, I used distillate methanol recovery of 99.5, which was specified, and distillate methanol stream purity of 99%. as the initial specification. The flow sheet is fully specified at this point, and we are ready to run the simulation. We already done that. So from the given description, it should converge easily, and it did converge, though I made some mistakes, and that it does happen. You just need to know where to look, you know, to troubleshoot if it doesn't converge. And as a novice designer, or if you're new to simulation, you need to take some time for you to know where to look for problems, right? And sometimes you need to configure more advanced situations, and I'll do a presentation on those too. Obtaining the final results. We have done that. Having the column to converge is not enough to call the distillation column model finished, right? The parameters should now be adjusted to receive the required product quality, of which we did receive the required product quality, and optimize operational conditions and energy consumption. So you have to know that we did manage to get the required product quality, but we did not optimize the operational conditions and energy consumption, which means our feed stage is not optimized. You know, the pressure, we just assume we used 1 atmosphere, but can we actually reduce that pressure and use vacuum pressure, you know, so that it becomes more optimized. Also, the number of stages, they are not optimized. You just guess from number 30, which is, you just assume those number of stages usually to make your flow sheet converge, right? So therefore, once you obtain a converged solution, you should change the specified variable so that the product specifications are met. In this case, we don't have to do that because, as I said, we did meet the product specifications. We didn't, though, optimize the operational conditions and energy consumption, and I'll do that in the next presentation. It is always a better way to adjust one variable after another, so there are not too many disturbances in the calculation, and converged solution isn't lost, right? You try to change many things, your convergence might be lost, right? And you get into trouble. So other general considerations and adjustments to be done. The easier the separation, the fewer trays are required, and the lower is the required reflux ratio. So if the separation is easier, you need lower energy consumption. So those parameters need to be explored and adjusted further. As I said, I'll do it in the next presentation. The higher the desired product purity is, the more trays are required. The lower the pressure, right, the less energy is needed for separation. That's why I said, instead of us using 1 atmosphere, can you reduce that pressure to vacuum conditions? Even though we incur like increased capital costs because you need to purchase the vacuum system, right? But that will be saved on the operational costs and also energy costs. So the lower the pressure, less energy is needed for separation. So also adjust pressure accordingly. So results discussion. Did you achieve the distillate of 99%, the recovery of 99%, 99.5%? Right, we'll go back and check that. All right, as I said, my bad, it's 99%. I put 99.5, but we needed 99%. So I'll go back there, change that. Symbol is no issue. Press edit here. It's no issue at all. Okay, so I'll go back to my column specs. Instead of, I'll put 99 white char. It should give me, it shouldn't be because it is already converged, so it shouldn't take long. What did I do? Solving, okay, there we go. Now we have, we said we wanted our stream purity to be 99% methanol. Here is there which is in stream 2, our distillate 99%. Also, we wanted 99.5% of this 3,200 to go to the stream 2. So what's second here? So we'll come here and say, we use the calculator and say 99.5%, which is 99.5 divided by 100. Right, is equal to that. Then multiply by 3,200. We want to see if that 3,200 recovery is achieved. 5.3. Right, there we go. So we need to have 3184. Is that what we have in S2? 32 is slightly lower, 99.5%. By 3,000 by stream S2, we need, oh yeah, it's right. We need 3184. So we also achieved our recovery. Boom. So we'll go back there and see what's up. It's easy peasy. Also, we're told that the approach temperature. So I said I'll define to you what it is. It is the difference between the leaving process fluid and entering service fluid. Remember, your condenser is simply its heat exchanger. So the water is coming in, and also we have the process fluid coming in. So it's cooling that process fluid. It's condensing. That's why I call it a condenser. It simply condenses those vapors, right? So we say it's the difference between the leaving process fluid and the entering service fluid, which is our water here. So the question gives us that approach temperature control, this should be greater than 20, but less than 90, right? We are given that cooling water is at 30, right? So which means our vapors needs to be more than 30 degrees Celsius for us to use water as a cooling sink. Is that true? Let's go and check our stream. You should know that the temperature of this stream is same as the temperature of this stream, right? Because it's simply condensing. It's a vapor at the same temperature. It's a liquid at the same temperature. So it's a liquid at its bubble point. So what's this temperature, which is the same over here? Is it above 30 for us to be able to use water? So I'll click here. Filling, I'll change to degrees Celsius. Remember, our water is at 50. So yes, it's 64. So it's water. So then we can use water as a cooling system. Bam. I'll turn back this to all right. And let's go back here. So our condenser temperature is at 65 actually. Therefore, condenser temperature approach is 65 minus 30, which is 35 degrees Celsius, which is greater than the 20, which is our minimum constraint, and also less than 90 degrees Celsius. Hence, condenser temperature approach constraint is met, right? Also, we are given that we have two types of available steam. The one at 25 per square inch gauge, and the other one is at 100, right? So you go to your steam tables, you find what's the temperature of this 25 per 6. So I found this one is 130 degrees Celsius, and also the temperature of 100 per 6, it's 170 degrees Celsius from the steam table too. So here's the deal. Okay, we'll go back here. I'll show you something. Let me see. Okay, so for us to use steam as a heat source, to heat up this liquid at its bubble point. So this is liquid at a bubble point. We need steam to be at a higher temperature. That's the requirement. The steam, it has to be at a higher temperature, so that it's a heat source, right? So let's go back to our presentation. So boiler temperature is 104. How do you get that? Good question. Remember, temperature in here is the same. So we click here, temperature in degrees Celsius is 104. That's how I got that 104. Okay, so it's 104. So steam temperature should be greater than rig boiler temperature, so as to provide heat to the rig boiler, right? So both available steams are candidates because they are both above 104. But also we have a temperature approach constraint. So for the 25 P6 steam, what's the temperature approach? It will be 26. It is greater than 20, but it's less than nice. So it's a valuable candidate too. For the 100 P6 one, it's 66. It's still a candidate. So both steams, let me do this here. So both steams are candidates, but I chose the 25 P6 steam as lower pressure steam is cheaper to produce. It's much cheaper for you to produce 25 P6 steam from the rig boiler as compared to the 100 P6. So by doing this, I'm also saving energy and making sure that our profit becomes more, right? So on the next presentation, we will optimize these operational conditions and energy consumptions. So if you have any queries or questions, please contact me on tubasband@gmail.com. Please like, subscribe, and comment on YouTube channel. Also click the link on the description to support my t-shirt sales business. I have to tell you, this Coco is an open software simulation program. So you can get it for free online. And there are many YouTube videos, you can even take examples from Aspen Plus and apply it to Coco. It is a nice simulation program and I love you so much. You guys take care. I hope you enjoyed my presentation. Be lit. Thank you.